Good morning, everyone. What I'd like to talk about in today and tomorrow's lectures, I want to pose the question, in what cases can simple auctions perform well even in complex settings? So today the plan is to talk about positive results. So we're going to identify conditions on preferences of bidders in an auction such that simple auctions are near optimal at equilibrium, even though the setting will be fairly complex. And then tomorrow we'll talk about impossibility results. So how under sufficiently rich preferences, bidders in an auction, in fact no simple auction can have good welfare guarantees. If the stuff I talk about sort of piques your interest, I'll be drawing primarily on a survey that just appeared a few months ago with Vasilis Tsirkanis and Eva Tardos called The Price of Anarchy in Auctions. And needless to say, please jump in and interrupt at any time if you have questions or if anything's unclear. So the representative complex setting that I'm going to use for both of these lectures is a standard model of multi-item auctions. So probably many of you have seen this before. It's a standard model for analyzing combinatorial auctions, for example. So it's a market that's going to have m indivisible items, for example, licenses to use wireless spectrum. And there's going to be n bidders in the market. Okay, so for example, telecom companies bidding on these licenses. And we model preferences by a private valuation. So each bidder I will have a valuation function VI, which says for any possible subset S of items that bidder might acquire, what is their value for it? We're going to look at quasi-linear bidders, so they just want to maximize their value minus what they pay for the items acquired. And we're always going to be thinking about the objective of, in these talks, of welfare maximization. So in a perfect world, if we could, we would love to allocate the items amongst the bidders to maximize the sum of their values for the items that they receive. Okay? Now, when you first see this, so suppose you wanted to solve this problem, welfare maximization with private preferences. Some of you may naturally think about something like the Vickrey-Clark-Groves or VCG mechanism, which is actually a very general tool that can be used to solve any social welfare maximization problem in dominant strategies, including this one. And so in these talks, I'm not going to be thinking about the VCG mechanism or any other direct revelation mechanisms. Remember, the first step of the VCG mechanism is you ask bidders to report their types. Why am I not going to talk about direct revelation mechanisms? Well, think about what that would actually mean. So how many private parameters does a bidder have to specify in principle in such a setup? 2 to the m different parameters. Okay, so one value for each of the 2 to the m subset of items that they might receive. And 2 to the m is growing very quickly with m. If m is 10, this is like 1,000 parameters. If m is 20, this is like 1,000,000 parameters. And so that's why you don't see direct revelation mechanisms in practice for multi-item auctions with a reasonable number of items.
But in some settings, and perhaps in many spectrum auctions, a bidder need not report all of its combinations because some combinations are completely irrelevant. So is it clear that practically speaking it's impossible to run a VCG auction for the spectrum setting?
Good. So the question is, let's drill down on this. Could you really run a VCG mechanism? It kind of depends on the assumptions you'd be willing to make. So if you're willing to assume, and I should say, we'll be thinking about lots of different assumptions on these valuation functions. When I say bidder preferences, what I really mean is what structure are we assuming here? And if you impose strong enough structure, then in fact you might be able to succinctly describe your preferences. Okay, so for example, later we'll talk about unit demand bidders, where you only want one item. There, it's not difficult to describe all of your private information. It's just one number for each of the items. So it's m parameters instead of 2 to the m parameters. So the VCG mechanism could be used for unit demand bidders, or if you sort of insisted that bidders act as if they were unit demand, is really the way to think about it.
But there might be just a few combinations that they're interested in.
Sure, right. So, and let me again draw a distinction, because it's a good question. So you go beyond that. But so I think there's a fundamental distinction between whether you think you know in advance, what's the important subset of players' valuations, and you can actually build that into the auction format, into the bid space. And then that's what you sort of need for a direct revelation version to be practical. A different one would be say, well, let's design a so you have ascending bundle auctions which kind of have this form, which in principle, it's expressive enough that bidders can report an entire 2 to the m length valuation, but hopefully on practical instances will only need to elicit a very small subset of their valuation in order to achieve an efficient allocation. So that in effect is still, so it's not it's only direct revelation in pathological cases. Normally you stop early. Yeah, all of these are good distinctions. So we'll be looking at, and so we just talked about, one way to make VCG mechanisms practical is restricting the message space. And so we'll talk about to what extent, when that can work and when that can't work. Okay. All right, so we're not going to talk about direct revelation mechanisms. So what do people actually do? Right, people do run multi-item auctions. So let me turn to the spectrum auction literature, which we just discussed. That's probably one, if not the biggest killer application of multi-item auctions. And so these are auctions which governments run to allocate off the rights to use wireless spectrum to the highest bidder. And these have been used in many countries for several decades. And pretty much since the beginning, so since auctions were used in the early 90s, the workhorse in spectrum auction design has been simultaneous ascending auctions. Many bells and whistles have been added over the years, but still, this is the sort of building block on which everything else comes from. So simultaneous ascending auction, all I mean is you run an ascending English auction for each of the items for sale, all in parallel. So from a bidder perspective, you have these M items that are being sold. At any given moment, you're picking which subset of the items you still want to be in play. Not necessarily. What I mean is that you are sort of, if you think about raising your hand at an English auction, here you basically have M hands, and you pick which subset of the M hands you want to be raising at any given time. Okay? And you could coordinate the price increases across these auctions or not. I'm going to be agnostic to that. Okay, so the point is that you're participating simultaneously in all of the auctions, as opposed to, for example, running an auction for the first one, then running an auction for the second one, then running an auction for the third one. So that would be a sequential implementation.
So it's not entirely, you cannot enforce simultaneity.
Okay. All I'm interested in is that bidders participate in all of them at the same time. All of the still active auctions at the same time. Yeah. Good. So this is what people use. All right. And nobody thinks they're perfect. Nobody out there is saying simultaneous ascending auctions achieve fully efficient allocations. Okay? Nobody believes that. Why not? There are well-known reasons for inefficiency in simultaneous ascending auctions, even in very simple settings. So let me just briefly recap a couple of the... Yeah.
What is the stopping rule in the simultaneous auction?
We're not going to go into that level of detail. So this is all just for motivation here. So.
Okay. So, but it's not necessary that we stop raising prices on one auction, the activity stops there. It may continue...
So you can imagine lots of different details for activity rules and a sort of final round. None of that's going to be salient for the points I'm making here. Yeah. So this is all just this is a preamble just to explain why. Right. So all of the theorems are going to be about quantifying inefficiency in auctions. So the purpose of this preamble is to point out that in real auctions, the ones that people really use, there is indeed inefficiency, and it's an interesting question to think about: is it a lot of inefficiency or is it not very much? So those are the points I'm trying to communicate right now. Okay, so one source of inefficiency in these auctions is demand reduction. So this is when a bidder will acquire fewer licenses than what it actually wants in order to get them at a cheaper price. And the easiest way to understand this is just an example, very simple example. So imagine there were just two items, right? So maybe there's a license for Northern California and then another one for Southern California. And imagine there were just two bidders. Let's say there's a big bidder who's happy to have one or both of the licenses and is willing to pay $6 for each of them. And then there's a small bidder who only wants one of the licenses and is willing to pay $5 for either one, doesn't care which one. Okay? So imagine now you sold these two licenses in simultaneous ascending auctions. Okay? Imagine you were bidder 2. Okay? You want a license, you're willing to pay $5. If you're bidder 2, you're not going to drop out of this auction until the price of both items has reached $5. Up until that point, you're happy to stay in. You might get a license for a price less than $5. At that point, if bidder 1 has stuck around, it wins both of the items, which is the social welfare maximizing outcome, and it gets a value of 12 and pays 10 for utility of 2. Okay? So that's what would happen if bidder 1 behaved truthfully, in the sense that it stayed in the auction as long as its values dictated. What else could the first bidder do if it wanted to have a higher utility? Well, it could pretty much immediately give up on item number 2, say. Okay? So let the second bidder take Southern California, and then the second bidder will be happy with that and leave the first bidder to get Northern California. They'll both pay a price of approximately 0. Okay, so there, it only gets 1 license, bidder 1, for a value of 6, but it pays nothing. Its utility has gone from 2 to 6. Okay, so it got fewer licenses, but at a radically cheaper price. So that's demand reduction. A second issue, which is more relevant for tomorrow than today, but let me mention it here, is the exposure problem. This arises when there are complementarities between items, so synergies between items, where your value for receiving an item depends on also getting others at the same time. For example, let's switch our big bidder so that now it's only interested in getting all of California, both north and south. Otherwise, it has value 0. Say it has value 6 for both. Bidder 2, same as before. Either license is fine for a value of 5. Okay? From the welfare maximization perspective, we'd again like to see bidder number 1 win. Right? We can only make one of them happy. We'd rather make bidder number 1 happy. But that's unlikely to happen. Again, bidder number 2 is not going to drop out of simultaneous ascending auctions until both prices have reached 5, at which point that price of 10 is far more than what bidder 1 would be willing to pay. Okay? So bidder 1 is exposed because, in effect, this mechanism doesn't give the bidder the vocabulary to express the fact that its preferences have these complementarities across items. Okay? All right, so these are well-known inefficiencies. Are they a big deal? So on the next slides, let me show you some sort of quotes from economists that have really worked in the trenches for many years. Okay, so they've done both theory and practice around spectrum auctions. So let me start with some quotes by Peter Crampton. He's done a lot of work in this space. Already the first thing he says, I think, is sort of very remarkable, which he says, spectrum auctions and more broadly multi-item auctions, it's too complex to have any ambition of full efficiency, to have a welfare maximizing solution. Okay, so he up front sort of admits that full efficiency is probably not something you're going to achieve. And for that reason, when we get to theorems, I will never be striving for theorems that guarantee full efficiency, okay, because that's not what we see in the actual mechanisms. He goes on to say that there's pretty clear evidence of demand reduction, okay, in the auctions that were being run back in the 90s. And he concludes that, yeah, there was demand reduction. Yeah, it introduced an inefficiency. We didn't get full efficiency. It's not a big deal. Okay, the inefficiencies were small. All right? So that was the claim from looking at the data. For the exposure problem, so this now is not a field study. This is a lab study by Ausubel and Milgram. But so they looked at simultaneous ascending auctions. And what they did is they gave, it was a lab study, so they gave people fictitious valuations, artificial valuations, and they slowly increased the strength of the complementarities. Okay, so how strong the synergies were across different items. And what they discovered was that simultaneous ascending auctions performed worse and worse as the complementarities got stronger and stronger. And in fact, you had some very poor, very inefficient outcomes once you had very strong complementarities. And so the takeaway from this paper was that simple auctions like simultaneous ascending auctions do not seem good enough with strong complementarities, and they were using that as a jumping off point for advocating package bidding. Okay? So to summarize, what's the takeaway from these quotes? There's a rough consensus. You get some different opinions, but there's a rough consensus from experts who work on spectrum auctions that this is what's sort of true. This is the ground truth about simple auctions, okay, for multi-item auctions. So first of all, if it's largely a substitute setting, so if you do not have strong complementarities between items, then simple auctions work pretty well. This was like the Crampton quotes about demand reduction not being a big deal. On the other hand, if you do have strong complementarities, you really need more complex auctions. Otherwise, you might suffer from very poor welfare outcomes. Okay? So the point of these two talks is to prove theorems which map quite directly onto both of these two folklore beliefs. Okay, so translations of these beliefs into rigorous mathematical statements. Now, if you think about what these are saying, both are saying, look, this is a setting where an auction is not fully efficient, but in one case, it's not too inefficient. In the other case, it's really inefficient. Okay, that's what these say. So that's fundamentally a statement about approximation. asking to what extent the equilibria of auctions approximate the best case scenario of full welfare. And for that reason, because these are fundamentally about approximation, if you look in the traditional economic literature, you do not, as far as I know, really see statements that map directly onto these kinds of statements, because approximation just hasn't been widely used in the economic literature thus far. Okay?
When they say work pretty well,
Yeah.
do they always mean efficiency or do they mean revenue maximization?
It depends. In the context of the specific Crampton quote that I listed, it was in terms of efficiency. It was in terms of welfare. He also goes on to speak about the revenue properties separately about those auctions. So they do care about it, but I'm just going to focus on the welfare aspects. Yeah. Okay. And so it turns out that computer scientists have been thinking about approximation guarantees forever, basically because there's lots of computational problems that are too hard to solve exactly, and you have to resort to heuristics. And to analyze heuristics, we've developed a sort of theory around approximation guarantees. And it turns out that language is perfect for translating these folklore beliefs into mathematical statements, into theorems. And so that's what I'm going to show you across these two lectures. Okay, and again, today we'll focus on theorems that correspond to the first one, possibility results. Tomorrow, the second one, impossibility results. Okay. All right, so just to give you a little sense of where we're going, it's okay if not all the words on this slide make sense, or if you're not quite sure how to interpret this theorem, we'll come back to it. But I still want to give you some sense of where we're going today. Okay, so this is also where we'll conclude the lecture. So this is a theorem which I think maps quite directly onto folklore belief number one. Okay, without strong complements, simple auctions work pretty well. So in the theorem, how do you encode without strong complements? That's encoded with an assumption about bidders' valuations, okay, structure in their preferences. Okay, so the word here is submodular. It's okay if you don't know what that means. I'll tell you later. Basically, it's just a set theoretic analog of concavity. Okay, so it just means diminishing marginal values of additional items. So that's a version of having no strong complementarities. You have these diminishing returns of getting more items. So that's where that's encoded. And then where is it encoded that it works pretty well? It works pretty well in the sense that every equilibrium is within some constant fraction. It turns out it's 63%. And believe it or not, that number is going to be showing up over and over again today. It turns out to be something pretty fundamental about it. So every equilibrium, it's not 100% of the maximum possible social welfare. We never expected it to be. You can have demand reduction, for example. But it is within some uniform constant bound, 63%. Uniform in the sense that the number of bidders can go to infinity, the number of items can go to infinity, and you can look at any kinds of prior distributions that you want. Okay, so what's the equilibrium concept? The equilibrium concept is Bayes-Nash equilibria. That should have you asking what's the prior, and it can actually be an arbitrary prior as long as bidders' valuations are independent. Okay? And the 63% is uniform over all three of those things: number of bidders, number of items, and the assumed prior distribution. Well, I understand if this is mysterious, the 63%, and you're not sure how to interpret it. We'll talk about that as we go along. Okay? But this is what I mean by a theorem, which is a translation of the folklore belief. Under suitable assumptions on preferences, every equilibrium is within a reasonable constant fraction of the best possible.
Identical items, or they need not be?
Need not be identical. Yeah.
Independence is a strong assumption in the context.
We'll have some results for correlated as well, but but we'll also have some counterexamples for correlated. So we'll talk about that. Okay. It's largely an open question to figure out how much this can be relaxed and still get statements of this form for this level of generality. Okay.
The spectrum context.
Say it again?
It's the spectrum concept.
It's true.
It's a very small.
It's true. I do want to point out, a lot of auction theory assumes independent valuations when it's probably not accurate. So it's in that tradition a little bit. But as I said,
You started with a certain context, but anyhow, go
I agree. Good. Okay, so this is where we're going. And so I'd like you to be kind of maybe impressed with this result, okay, on a couple levels. A couple I've already said. First of all, that it does map so directly onto the folklore belief. Secondly, that the 63% is independent of all of these different parameters which you're quantifying over. What was the third reason I wanted you to be impressed? Oh, I remember. So the third thing is this, so we're talking about the equilibria, Bayes-Nash equilibria of multi-item auctions. Nobody has any idea what those equilibria actually look like, okay? So no one knows how to characterize the Bayes-Nash equilibria of a multi-item auction, okay? And I think that's another reason why the traditional economics literature hasn't so much talked about results like this. It's because most, the tradition is you first characterize the equilibria, you figure out what they look like, and then from that you deduce all kinds of interesting properties, one of which might be a welfare guarantee, and then probably a lot of other properties as well. Here, somehow we're going to bypass the need to characterize what equilibria look like, and yet despite that, despite not really understanding what they look like, you can still prove these guarantees on their welfare. So I think that's another interesting aspect of these results. Yeah.
Why do they consider first price and not second price?
Good question. Yeah. So in general, almost everything I say in these couple lectures will be more general, and there'll be lots of different variations on the results which are true. So there is a version of this which works for second price auctions. There's a version which works for all pay auctions. This number does change, and sometimes it's not clear to what extent that's fundamental and to what extent just our analytical toolbox isn't sharp enough. So I'm going to focus on first price auctions just because the story will be very clean if I do that.
But in this theorem, what would the number be for second price?
Second price, we don't know the answer. I would speculate it's still 63%, but we don't actually have a proof of it. Yeah. So there's just an open mathematical question there about what's the right number. Yep.
Is there any hope for a sort of research program to sort of provide a definition of what it means for an auction to not be too complicated, and then look at the class of auctions and compare balance across this?
Absolutely. Great comment. And that will actually be essential for tomorrow's lecture when we talk about possibility results. Because here, for possibility results, I just have to exhibit one evidently simple auction format and prove a good guarantee for it. In a possibility result, I really don't want to just have a negative result for one particular auction format. I want to say all conceivably simple auctions you could define will not perform well. That requires a definition of what makes an auction simple or complex. Fast forwarding a little bit, so there's many measures that people have been thinking about over the past few years. We'll basically be using the dimension of the message space. That's what it'll turn out to be tomorrow. Yeah. Mm-hmm.
So you say that it's not enough to characterize the space of equilibria, so isn't it too optimistic to expect that the system will be in equilibrium? And maybe in practice the system will be in another state,
Yep.
which is not in equilibrium, and then this is not valid.
No, that's a great comment. So, and to be honest, computer scientists have been very critical of equilibrium analysis because of sort of our particular set of biases about the way we're trained. And so, there's been a lot of work, largely in computer science, which exactly says let's look at sort of good properties of Nash equilibria or something like that, and let's see how robust they are. So, for example, what if I replace the assumption of convergence at a Nash equilibrium to just uncoupled dynamics, where people are doing some kind of regret matching strategies or something else reasonable? And so it turns out this will be true for pretty much all the positive results I say today. You can relax the assumption that you're at an equilibrium and replace it that bidders are at least doing something locally reasonable, like a regret matching type algorithm. I won't have time to talk about any of that, but actually the machinery that's used to prove those guarantees for more permissive equilibrium concepts is pretty much the same machinery I'm going to develop for this. Okay? Yeah, so I think it's a great comment. Okay, great. Okay. And so the other thing which is going to be cool is that actually we will deduce this result either today or maybe it'll spill over into tomorrow from a very modular and user-friendly analytical toolbox. Okay, so I'll develop a few tools over the next hour, and just putting them together will actually just imply this result. Okay, so you get very powerful conclusions, but in some sense it's very easy to derive them given advances in the last few years. Okay, so most of the points that I want to make, most of the machinery I need to develop, I can already do in single item auctions. Okay, so we're not going to talk about multi-item auctions for a little while, just single item auctions, first price. There's already a lot of interesting things to talk about. Okay. All right, so I'm sure you've seen first price auctions a few times in the summer school, I think. So going to be looking at the private value model. So one item and bidders, private values for winning, quasi-linear utilities. So how do you reason about behavior in a first price auction? Nobody's going to bid truthfully, right? That would give you zero utility. Everybody's going to shade their bid. How much do they shade their bid? Well, it sort of depends on what they believe other people are doing, okay? How other people are bidding. And so we'll model that in the standard Bayesian way. So there's going to be uncertainty. So players have uncertainty about each other's valuations. That's encoded by a common prior distribution. We'll think both about the independent private values model, but also the correlated private values model. Both of those are going to be interesting to discuss. So so the equilibrium concept is just a Bayes-Nash equilibrium. So a strategy is now not merely a bid. A strategy is a whole kind of plan. Given what your valuation is, how would you bid? How much would you shade? So that's a strategy, and a Bayes-Nash equilibrium just says that every bidder bids optimally given the information available to them at the time that they have to choose what to bid. So if you're a bidder, what do you know when you have to commit to a bid? You know your own valuation. You know the distribution from which others' valuations were drawn, possibly conditional on your own valuation if it's not independent. And you know the strategies. So you know the distribution over others' values. With their strategies, it induces a distribution over bids. So there's a sense of a best response. And so that's all it says. Everybody's best responding given the available information at that time. All right, so if you haven't, some of you I'm sure have thought a lot about Bayes-Nash equilibria in the past. If you haven't, it may seem a little abstract. But for first price auctions, at least if you're in the symmetric world, by symmetric I mean the valuations are IID, sampled from the same distribution, then actually Bayes-Nash equilibria are relatively easy to characterize and interpret. So for example, let's imagine everybody's valuations was drawn IID from the uniform distribution, 0, 1. Okay? Then a standard calculation, you can find it in any auction theory book, tells you exactly what the unique Bayes-Nash equilibrium is. It's a symmetric equilibrium. Everybody uses the same bidding function. And the bidding function depends on the number n of bidders. And you shade your bid by this factor of n minus 1 over n. Again, n is the number of bidders. So if you're facing only one other bidder, at equilibrium, you will bid half your value. If there's two other bidders, at equilibrium, you will bid 2/3 of your value, and so on. So the stronger the competition you face, the less you will shade your bid, as you would probably expect. Okay? And this is not just about the uniform distribution. There's an analogous statement for any IID setting. One thing, so it's great having such a crisp understanding of what equilibria look like in the symmetric case. But another thing that's really cool is here we actually do get full efficiency, by which I mean the bidder with the highest valuation will always be the winner. And the reason for that is just that everybody's using exactly the same bidding strategy, and that bidding strategy is strictly increasing in the value. So the highest bidder will be the highest value, and that'll be the winner. Okay? So full efficiency and well understood Bayes-Nash equilibria in symmetric first price auctions. All of this goes away if you drop the symmetry assumption. Okay? For example, what if we just make one of the two bidders, one's uniform 0, 1, the other uniform 0, 2. Okay? Here you can actually, with a little work, derive what the Bayes-Nash equilibrium is. And once you do that, you see that actually the equilibrium is not fully efficient. Okay? Or equivalently, there are cases where the bidder with a higher valuation will actually be the lower bidder and therefore lose. That's what it means to not be fully efficient. And we already see the intuition for why that's true, right? So from the symmetric exercise, we see the amount you shade sort of is less and less as your competition gets stronger and stronger. So from the bidder number one's, the weaker bidder's perspective, it's facing competition which is stiffer than as if it was in an IID environment. So it's going to bid more aggressively than it would in an IID case. Whereas from the second bidder's perspective, it's facing weaker competition than a second identical copy of it. So it will shade more than it would in the IID case. So that creates opportunities for inversion and therefore efficiency loss. So here you can derive the Bayes-Nash equilibrium, but I don't want you to sort of think that that part is general. So we really, in general, solving for the Bayes-Nash equilibrium is solving for a solution of a bunch of PDEs, and it's often not very easy. And we don't have a super great understanding of what these equilibria look like in general in asymmetric first price auctions. Okay? All right. So everything on this slide was already known to Vickery. We've known this for a long time. If you actually drilled down on this example and looked at the magnitude of the efficiency loss, it would be not very much. Okay? It's true you wouldn't get 100% of the maximum expected welfare, but you wouldn't be very far off. It would be a small enough loss you'd be tempted to ignore it in sort of a practical situation. So that motivates the question, how severe can inefficiency be in a first price auction? So next example, this is a much more recent example from a few years ago, and this is going to be for correlated private values. Okay, so we'll get back to the independent private values case later. All right? But let me show you a more severe example, interesting example for correlated private values. 3 bidders, First bidder, common knowledge, its value is 1. Okay? The correlation is between the second two bidders. Okay? They, with probability 1, have exactly the same valuation. And that common valuation is drawn from some distribution. Okay? The distribution, I'm not going to sort of go through lengthy calculations, but just for completeness, this is the distribution function of the distribution. So what does this say? What this says is that bidders 2 and 3 both have value 0 with probability 1 over e. E here, by the way, is the base of the natural logarithm, 2.718, et cetera. So with 1 over e probability, they have value 0. Otherwise, they have value drawn from some distribution on a support between 0 and 1 minus 1 over e. Okay? So whatever, some correlated distribution. Pretty obvious what full efficiency means, right? So bidder 1 always has the highest valuation. We'd like to see bidder 1 always win. However, in Bayes-Nash equilibrium, something different happens. Okay? Bidders 2 and 3 are going to bid truthfully. That shouldn't surprise you because each one knows that the other bidder, its sort of doppelganger, has identical valuation. So they're guaranteed 0 utility. The first bidder, however, okay, let's assume ties are breaking in favor of the first bidder. The first bidder actually may as well bid 0 because there's a 1 over e chance that bidders 2 and 3 also bid 0 and will break ties for bidder 1, giving it an expected utility of 1 over e. You can check with this particular distribution for any other bid that bidder number 1 might make between 0 and 1 minus 1 over e, its expected utility would still be 1 over e. It would win with higher probability, but it would pay more as a result. And the distribution is set up so those two effects cancel each other out. And a computation, which is easy, but which I won't do, is that so here we have inefficiency. That's clear. It's clear bidder 1 will not always win. And here we actually get a significant degree of inefficiency. Turns out the expected welfare of this Bayes-Nash equilibrium is 1 minus 1 over e. And in these talks, whenever I write 63%, what it actually always means is 1 minus 1 over e. Okay? So this is the second time that we've seen it. We saw it first in the statement of the theorem at the beginning that I promised I would prove to you by the end of the lecture. And now we see it arise again in an example here already in a single item auction, albeit with correlated valuations. Okay? Okay. So mostly I'm talking about single item auctions right now, but let me actually digress for a second. While we're I can't hear you, I'm sorry. If he doesn't, you probably have to perturb the example a little bit, but yeah. So you could still get numbers like this for different tie-breaking rules if you don't like this tie-breaking rule. This is for convenience of exposition. So, okay. So this is mostly we're talking about single item auctions, but while we're sort of seeing how this 63% comes up from all kinds of sources, seemingly coincidentally, let me show you sort of yet another way in which it comes up, this 63%. This is actually a much older example described by Engelbrecht and Wiggins and Weber. So it's going to be a more complicated setting in the sense that there'll be multiple items, but it'll be less complicated in the sense that it will be full information. So let's suppose we have n bidders, we have n items, and let's suppose that every bidder has value 1 for every item, okay? But it only wants 1 copy. Okay, so they're unit demand bidders. All right, and everybody knows this, full information. Okay? The mechanism, okay, as a bidder, you have to choose, this is by definition, you have to choose one of the n items and then choose a bid for that item. Okay? And then a first price auction will be run on whoever chooses to bid on a particular item. Okay? Pretty clear what the welfare maximizing allocation is. Each bidder should get a single item. That would be a total welfare of n. And for example, if you thought about pure strategy Nash equilibria, those would also have total welfare n. However, it's a symmetric game, so we know it better have a symmetric mixed Nash equilibrium. And what that symmetric mixed Nash equilibrium looks like, it has each bidder choosing an item uniformly at random. Okay? And then, whatever item you choose, now you know there's some random number of IID bidders, random number of other bidders there with you, and you just bid accordingly. Okay, so once you've chosen an item, now it's just a sort of normal, in effect, first price auction, albeit with a random number of bidders. Okay? And so why is this a Nash equilibrium? It's because, well, all the items are the same, right? So like if I think about what am I going to do, well, all n items have exactly the same distribution of how many other bidders are there and what they're going to be bidding, okay? This is not fully efficient, okay? So if you think about it, why is there an efficiency? There's an efficiency because there will be items that nobody selects. Okay, so basically, if everybody's choosing a random item to bid on, that's like taking n balls and tossing them uniformly and independently at random into n bins. Okay, so it's a very well-studied randomized process. You could ask the question, how many bins go empty when you toss n balls into n bins? And the answer is about a 1 over e fraction go empty. And that's your efficiency loss. Okay? So as n goes to infinity, the expected welfare of this equilibrium tends to 1 minus 1 over e. Again, 63%. Okay, seemingly for very different reasons. Okay, previously, we had a single item correlated values. Here we have multiple items with full information. Okay. Now,
63% of n, right?
yes, yeah, 63% of the optimal welfare n. Yeah, exactly.
But there are asymmetric equilibria
Definitely.
which attain full efficiency.
Definitely, yeah.
So is I can't remember, is the statement that you had at the beginning only true for
No, the statement at the beginning was, the positive statement was that every Bayes-Nash equilibrium is within 63% of optimal.
Okay.
Yeah. Now, you might hope to prove statements, and we'll see that there are senses, we're already seeing that there are senses in which that's, for that kind of guarantee, the best, the best fraction you could hope for. You can try to say, okay, for, certain equilibria, you will do better. And certainly this is a concrete example where you can say that. You can say for a pure Nash equilibrium, for example, you'll do better. There are other cases. The level of full-blown multi-item auctions, again, because we sort of don't understand what the equilibria look like, we don't really know where to get started of how to sort of have an equilibrium selection to have better bounds. But absolutely, for sufficiently simple settings, one should absolutely do that.
Which is the best equilibrium?
Say it again?
Which is the best equilibrium?
Which is the best equilibrium? Or?
So if what is the percent when you take the best equilibrium?
In this example?
No, in general, it is the Remy bound.
In general, in what auction game? I mean, what,
The same theorem, positive theorem you showed before.
yeah.
Instead of all equilibria, I replace it with there exists one equilibria such that the welfare is above.
I'd have to check. I believe it's still 63%, but I'd have to check the constructions. It would be sort of a detail of the constructions that people have come up with to prove tightness of that theorem.
So it's still not optimal. There are cases where no equilibrium is optimal.
Correct, for sure. And the impossibility results we talk about tomorrow will really kind of rule out any reasonable good equilibrium. Yeah. Okay.
I think your previous example, it must be that bidder 2 and 3, in the sense of that might be good enough.
Oh, so that's true. I think this is the unique pure Bayes-Nash equilibrium. I didn't check if it's the unique mixed one, but I could imagine, yeah, that already in this example, that would be my guess too, but I didn't prove it. So good. So this is maybe a
In fact, if you change the tie-breaking rule, you may not get an equilibrium at all.
right. Yeah, you got to be careful. I agree.
He has some results for correlated equilibrium.
Okay. Good. All right. So that's kind of a little homage to 63%, seeing how it comes up in a lot of different ways. It could be worse, right? I mean, there is a parameter here going to infinity. We could have imagined this actually going to 0% with n. And actually, tomorrow, when we talk about complex preferences, we will see exactly that. So again, don't forget, it's true it's not 100%, but this could easily be 0. But at least in this example, it's not. Now we want to turn and say, okay, can we actually prove that this doesn't go to 0 with a large number of bidders and items and general distributions and so on? Okay, so that's where I want to go next. Okay, so what these theorems are about is approximation guarantees for equilibria of games. Okay? And actually, computer science has been a little obsessed with that idea over the past 15 years or so. So just a quick aside to kind of explain how computer scientists talk about this endeavor, approximation guarantees for equilibria. So computer scientists like to use the phrase price of anarchy. In my experience, economists totally hate this phrase. They kind of look at me and say, I don't get it. Where's the price? Where's the anarchy? I'll explain in a second. So what's the definition? So it's defined by Koutsoupis and Papadomitriou, originally for full information games, but it works fine for incomplete as well. So suppose you have a game, complete or incomplete information. Suppose you've settled on an objective function, like say welfare maximization, and some equilibrium concept, Nash, Bayes-Nash equilibria, what have you. The price of anarchy is just the approximation of optimal that equilibria achieve. So you look at the ratio between our protagonist, how well an equilibrium does, and this kind of utopian benchmark. What would be the objective function value of the optimal outcome of the game? So the closer this ratio is to 1, the better. Okay, if that's 1, that actually says that equilibria are fully efficient. The closer it is to 1, in some sense, the more benign the consequences of self-interested behavior. Okay? Now, in the presence of multiple equilibria, you have to make a decision about which one to talk about, and there's many different choices that have been explored. For positive results, for guarantees, what you'd love to get away with is a guarantee for every single equilibrium. And so that would dictate looking at the worst, i.e. furthest from 1, value of this ratio ranging over all equilibria of the game. Okay, so that's the definition you want for the most meaningful positive results. If you can't get positive results with that strong definition, you can look at weaker definitions, and people have done that. But I won't talk about that this week. Okay? All right, so that's the price of anarchy. Oh, so why is it called this? So you have to try to remember what computer science was like 20 years ago, basically. So sort of before the internet had really sort of gone mainstream. So basically, computer science involved working only with environments that we built ourselves. Right? So we had a computer, we were writing an algorithm that would run on some standalone computer on our desktop. Maybe you had a network, but then you'd sort of have some distributed protocol, which you would assume that all of the machines would obediently execute. This was computer science, kind of pre-internet. And it's still a big part of computer science. But 21st century computer science, all over the place, a lot of our important applications involve strategic interactions between different parties, right? Auctions, lots of network games, and so on. So price of anarchy was sort of compared to the old normal of having full centralized control or full distributed control over your environment. So that's why it's called what it's called. Okay, and I'm only going to be talking about auctions in these 2 lectures, but I do want you to know that it's been studied in many, many different application domains across computer science, operations research, and economics. These days, it's not uncommon for someone to send me a title of a paper like this. This was about evaluating a proposal for decentralizing part of the UK health system, or even this. So, which basically encoded the strategic decisions of the passes and shooting between different players of a basketball team, sort of made an analogy with how routing works in a network. Okay? All right, so just a quick aside to let you know what this is called and that it's a big deal well beyond auctions. Okay? So in fact, the focus on auctions has only been really the last maybe 5 to 7 years. Okay, so for the first decade, it was really very focused on internet-type applications, so network games. All right, first price auctions. They can have inefficiency. How big can it be? Could we prove some kind of uniform guarantee? Okay, saying that first price auctions are approximately efficient. If so, how would we do it? So here's going to be at a high level idea, here's going to be the plan. All right? So we want to prove a theorem which says, in some sense, no matter what the distribution is, no matter which Bayes-Nash equilibrium you look at, the welfare of that equilibrium is close to the maximum possible. This is just a single item auction. So the maximum welfare, I mean, that's just the valuation, the highest valuation of any bidder, right? That's the welfare in a single item auction. So how are we going to do this? So remember, the price of anarchy talks about a worst case equilibrium. So we need to prove a guarantee for every single equilibrium. So we need to pick an arbitrary one. Further, remember, we're thinking about settings where we have no characterization of these equilibria. So the question, if we're thinking strategically about what this proof is going to look like, we need to ask ourselves, how are we going to use the assumption that we're working with an equilibrium if we don't even know what an equilibrium looks like? So pretty much all we have going for us is the definition. Okay, so in terms of best responses. Okay, at an equilibrium, every bidder is best responding to everybody else. Okay? So how would you use the best response condition in a proof if you wanted to say that an equilibrium was near optimal? Well, something you can do is you can say, well, pick a player, okay? Pick a hypothetical deviation. I'm going to call that a baseline strategy. So pick something else the bidder could be doing. Now you can lower bound the player's utility at the equilibrium by the utility they would obtain by this hypothetical deviation. Okay? So you can choose an I, you can choose a baseline, B star I, and then you get an inequality of this form. Okay? So that's kind of the only way I can think of to use the fact that it's equilibrium without knowing anything about what they look like. Okay, so this is going to be the building blocks for our welfare guarantees. So there's creativity here, right, as far as doing a proof. How do you choose the I's? How do you choose the B star I's? So for the I's, presumably you're going to use the fact that every single player is best responding. Okay, if there's some player doing arbitrary stuff, that could definitely screw up the outcome. So we should expect at least minimally to do this once per player. That leaves the question of how do we choose these baseline strategies. And that's a bit of an art. I'll show you some of the things that have worked well. One guideline is at the end of the day, we have to somehow connect this back to the maximum possible welfare. So maybe the baseline strategy should have something to do with that. So for example, maybe they should actually induce an optimal allocation of the item. Okay? All right, so this is sort of how we're going to use the equilibrium condition. And now there's again going to be some sort of artistic step where we take inequalities of this form. Oh, I should say, okay, so this isn't exactly what we want, but this feels like it's on the right track. Right? What are we trying to prove? We're trying to prove that the welfare at this equilibrium, we're trying to get a lower bound, okay, on the equilibrium welfare. That's not what this is, but at least gives us a lower bound on the utility of a player at the equilibrium. So it's on the right track, okay, pushing in the right direction. But still, we're going to have to somehow take all of the inequalities of this form and assemble them together to get what we want. What do we want? We want to say that the welfare at this equilibrium, meaning the valuation of the winner, is at least lambda, for some constant lambda, as close to 1 as possible, times the maximum possible welfare. And again, for a single item auction, this is just the highest valuation. Okay? So this step also takes some creativity. Okay? But again, we'll see an example. And so that's the plan. All right? This is the plan we want to execute at a high level. Just sort of aside, so in principle, when you execute this plan, you could imagine for each of the equilibria you want to prove a guarantee for, you choose a separate set of baseline strategies. That would be totally allowed if you just wanted to prove a guarantee for every equilibrium. Okay, fix the equilibrium, choose in response some baselines. We're going to be seeking baselines that do not do that. This is for technical reasons, but it's sort of a minor, it feels minor, but actually is what really drives the results I'm going to be discussing. So it's going to be important to choose the baseline strategies in a way which is actually uniform over all of the equilibria of the game. Okay, that'll become clearer as we go on. All right. Yes?
It seems that in at least some settings, the max possible welfare might not be the appropriate benchmark to use. For example, what if that's not achievable by... So does this mean... So the efficient outcome, for instance, may not be achievable in a certain environment. Is that something that you take into consideration?
Potentially, yeah. So this, so good. So thanks for the question, because I meant to say a little bit more actually back when I was here. Okay. So the question is basically, what should the denominator be? And I've proposed one thing, which is the best outcome from whatever your objective function's perspective is. You can do different things. I mean, one thing you can do is you can change the objective function if you don't like it. Another thing you can do, though, is you can say, well, so especially if you fail to prove positive results, you can make your life easier by replacing this with a sort of not as good number. Now, there should be some narrative for why the weaker benchmark is still motivated, but perhaps design constraints of the environment actually sort of pin you down to kind of a weaker benchmark. Okay? And so that reminds me of something else I wanted to say actually about this definition, right? So, when economists see these 63% guarantees and this kind of thing, usually a very reasonable question is asked, which is, how should I interpret this 63%? And is it big or is it small? Obviously bigger is better. Right? I think we can all agree on this. But how high is high enough? All right. So there's no correct answer to that question. But let me just give you a couple analogies. Right. So first, let me give you a mechanism design analogy. So just like here, you could ask how big a number is big enough. You could ask how strong an incentive compatibility guarantee is strong enough. Is it good enough to just have Bayesian incentive compatibility? Would you instead want strategy proofness? Or maybe you even want to go all the way to obviously strategy proof? Where do you stop? Okay, well, so how do you answer that question? Basically, you get the strongest statement you can while it's still being true and not compromising too much on other axes, okay? So theoretical research, so you prove your possibility results, you get a certain kind of incentive compatibility guarantee, and if you fail to achieve some stronger one you might want, you prove there's a reason for it. Okay, you prove that actually there is no mechanism meeting certain criteria with that stronger incentive compatibility guarantee. So that is one of the ways that you justify something like 63%. You just prove you cannot do any better. That is the theoretical limit of what is achievable. Okay, so the second analogy I'll give you is a sports analogy. So, is this 63% high or low? So if you follow any sport, one of the key statistics is your winning percentage. So of the games that you've played, what fraction have you won? That is a ratio exactly like this. The denominator is the utopian ideal of winning every single game, okay? So suppose you won 63% of your games. Is that high? Should you be impressed? Kind of depends. Depends on the context, depends on the sport. So maybe there aren't too many baseball fans in the room, but in baseball, if you told me that my team won 63% of their games, I would be jumping for joy. It would mean they were one of the best teams in the league and would have a good chance at the World Series.
So here, everyone wins 73% of
Right, so it doesn't have the zero-sum aspect. I agree. So there's a weird analogy that there's no zero-sum, but still. Right, so the point is, so in baseball, 63% is super high. In basketball, it's still pretty good. Your team's going to make the playoffs, but you're probably not going to win the championships. Okay, you just tend to see much higher winning percentages in basketball. So the point I'm trying to make is, all of that is because we have, a lot of practice seeing what happens, with outcomes in these sports. So the point is the context matters. You get used to what the high numbers tend to look like, what the low numbers tend to look like. We now have a lot of experience with these price of anarchy guarantees, and based on that experience, 63% is actually quite a good number. Okay, we rarely actually see guarantees, even in very simplistic settings, which are much better than that.
One question would be like, what are the environments that make this bound actually bind in a sense? So how likely is it that I really lose 37%, or are there some natural restrictions where I get this bound up maybe to 80% or whatever? Absolutely.
Right. So in general, whenever you have a worst case guarantee like this, you always want to go a step further and say, how do I strengthen my assumption so that I get a better conclusion? And in some sense, we'll see, we'll see sort of some examples of that tomorrow. I'm going to be going the other direction. So tomorrow we'll actually look at a weaker assumption, and the 63% will actually drop to 50%, but it'll handle a richer space of environments. But you could imagine doing it the other direction. Yeah. And same thing, like when you're doing constructions to show that something is impossible, you again want to simplify the construction as much as possible. Right? So maybe you have a lower bound not just for submodular valuations, but it even holds with unit demand valuations. And work in this literature, they do exactly this. So they're always trying to get not just sort of the worst case overall to match, but also the worst case in lots of different special cases to match as well. Okay. Okay, so back to trying to prove a game. So remember we had our plan. Okay, so we need to somehow choose baseline strategies. That lets us invoke our equilibrium hypothesis. Then we have to massage them into a welfare guarantee. Okay. All right, so let me show you how this is done for first price auction. Okay, and again, there are two parts. There are two creative steps. One is how do you choose the baseline strategies. Secondly, how do you massage the results into a welfare guarantee. Okay, so I'm going to show you those in two steps. So the key technical claim, I should have said, so ultimately we'll be interested in Bayes-Nash equilibria. Well, let's start with a full information case. As we'll see, the work that we do in the full information case will just carry over to the incomplete information case. All right? So this kind of inscrutable claim is going to turn out to be important for us. Okay? So we have a fixed valuation profile, fixed but arbitrary, first price auction. I claim that if you choose your baseline strategies properly, okay, so this is a one bid for each player, then it's going to be the case that for every single different bid profile, B, you have some lower bound on the total player utility when players deviate to their baselines relative to the optimal welfare up to a correction term, the revenue of the bid vector. Now again, let me remind you that some of these are really simple quantities given that it's a single item auction. This is just the highest valuation in the profile V. This is just the highest bid in the bid vector B. Okay, so these are just simple numbers. This is a multiplier, which will translate to our eventual approximation guarantee. And this is some inscrutable quantity for, at the moment. Okay? All right. So this is going to be a key claim. It's actually trivial to prove, so I'll show you the proof. Actually, before I prove it, let me show you why I would ever care about a claim like this. Let me show you why, if this claim is true, it naturally leads to equilibrium guarantees. Okay? So assume that we'd actually prove that claim. So this is just that exact same claim written again. So suppose we knew this was true for a first price auction. I claim then, for some constant lambda. Okay? So on the previous slide, I was claiming a lambda of 1/2. I claim that it then follows quite quickly that every pure Nash equilibrium of this first price auction, again, remember, we're thinking currently about the full information setting. There's a fixed valuation profile. Every pure equilibrium is at least 50% of the maximum possible valuation. Okay? Now, you might feel like complaining at this point, because you have a couple good reasons to complain. All right? The first reason you might want to claim about this alleged application is that first price auctions generally don't even have pure Nash equilibria. Okay, so it's not even clear what I'm saying here, right? So that would be a legitimate comment. The second one is that even, if the tie breaking is such that you do have a pure Nash equilibrium, actually you can prove it's going to be fully efficient. Okay? So any pure equilibrium, the highest value bidder will be the winner. Okay? So this is both about a concept that need not exist, plus the bound of 50% is way worse than what we actually know is true. Legitimate complaints. Why am I doing this? I'm doing this because the work we do here will extend, in some sense, automatically to the incomplete information case where we know that there is inefficiency. Okay? And we know that mixed Bayes-Nash equilibria generally do exist. Okay, so let's see why this is true. All right? So assume this is true. Let's consider a pure equilibrium and prove that it gets at least a lambda fraction of the maximum possible valuation. Basically, we just follow our nose. I mean, we kind of don't have much going for us, so we just kind of use all the ingredients in the appropriate order. So this is what we want to lower bound. Okay, so we fix an equilibrium. This is what we want to lower bound. What do we have going for us? We have the equilibrium condition going for us. So utility only drops if a player deviates from the equilibrium. So that means I need to be talking about utilities, player utilities. So I'll just split welfare into its two parts. The revenue goes to the seller, and the utility, what goes to the bidders. Here, I can apply the equilibrium condition. Okay? I'm going to apply it once for each of the bidders I, and I'm just going to apply it with the baseline B star I. Okay? The same B star I which is in the assumption. All right? So by virtue of being in equilibrium, the utility only drops. So I get this lower bound. Okay? Now by the assumption, I can take this weird entangled version of B star and B and disentangle it. I can lower bound this by lambda times the optimal welfare minus the revenue of the bid vector. These terms cancel out, leaving me just with lambda times the optimal welfare. Okay? And really, as usual, when someone's telling you about some mathematical statement, they're telling you in the backward order. Right? So how did this really come up? You want to kind of have a proof like this which works, and from that you reverse engineer that this is the kind of inequality you'd really like to be true. Okay? Yeah.
So you're in the top line, your lambda times optimal welfare. That welfare includes both the agents and the revenue going to the designer.
Well, so I'm thinking of the revenue just as a transfer between the bidders and the seller. So if you like, think of the seller utility as the revenue. So the sum of everybody's utilities is equal to the social welfare. Yeah. So this is just the maximum valuation of any bidder. Yeah. It's sort of zero. I mean, with respect to the payments, it's zero sum between the bidders and the.
Why didn't you say that the welfare equals revenue plus the sum?
So each of these utilities is a value minus a price, right? And this is the sum of the prices. Yeah. Cool. Yep. Say it again.
What's the assumption that it's pure?
I mean, I did not really use it, and so that's where we're going, okay? And I'm just using it. I didn't write any expectations on the slide. That's where we're going. Yeah. Yeah. Okay. I mean, what's nice, so I mean, here's what's nice. What's nice is that in the assumption, so in what we're going to prove on the next slide, the assumption is only stated for pure strategies. And at some point, we actually have to prove this. So that's going to make our life easier when we establish this inequality. Okay, but you're right, the conclusion will hold much more generally, as we'll see. Okay? All right, so inequalities of this form imply at least price of anarchy bounds for pure equilibria. So why is that claim true for a first price auction? Okay, remember this is the claim, lambda equals 1/2 here. So in particular, I have to tell you how to choose these baseline strategies. Okay, that's how these proofs work. Turns out to get 50%, a very simple baseline strategy works. Just bid half your value. Okay? So a bidder always could bid half their value if they wanted. So their equilibrium utility will be at least what they would get if they bid half their value. Okay? Why is this inequality true? Okay? Well, it's kind of trivial, but it's playing an important role. So let me just sort of step through it. So notice bidders are bidding less than their value. So all of these utilities are going to be non-negative. Right? This is just player I bids something less than its value. Either it wins or it doesn't. Either way, this is non-negative. So the only hard part is when the right-hand side is positive. Okay? So we can assume that half of the maximum valuation is at least the maximum bid in the bid vector B. Okay? So that's here. Now, if the maximum valuation is bigger than twice the highest bid in the bid vector B, then when this highest bidder, let's call it bidder number 1, when it deviates to bid half of its value, it will in fact be the highest bidder. Okay, so we're thinking about, we started from this bid vector B, and player 1 is deviating to half its value. And by assumption, that makes 1 the winner. When it wins, what's its utility? Well, whatever its value is, minus what it pays. It's paying its bid, half its value, leaving it with a utility of half its value. Okay? Which is, in particular is at least half the optimal welfare, even forgetting this correction term. Okay? So again, nothing to see here really. I just want to point out it's some simple algebra that leads to this, which then, as we saw, leads to the price of anarchy guarantee. All right, so now back to the 63%. So in this derivation I just did, it should have felt a little sloppy to you, like it was loose, right? Because somehow I need to prove this lower bound where I have this correction term, and I'm not even using that in this part of the proof. So presumably there should be some kind of trade-off I can do between the two different cases of the proof. And there is. And so that leads to an optimized version of that same technical claim where that 50% gets replaced by 63%. So the idea is to no longer just deterministic, so the baseline strategy will now be randomized. It used to be just bid half your value. Now it's shade your bid by a random amount, okay? Between 0 and 63% of your value according to some distribution. Okay, the details aren't important for us here. Okay, I just show you this to point out that it's simple. And then a computation does show that you get this result with the 50% improved to 63%. Okay? So chaining this with the derivation we had, we now got, okay, pure equilibria. Now we can at least prove they're within 63% of the best possible. Okay? All right, but what's really sort of the punchline here is that actually this 63% we just proved currently just for pure Nash equilibria, basically using the exact same argument, holds for Bayes Nash equilibria for any first price auction, any prior distribution, possibly correlated values. Okay? So 63, which we know is optimal. Right, we saw an example of a first price auction and a correlated valuation distribution and an equilibrium that really was off by 63%. This theorem implies that that is the worst possible example for any first price auction. Okay? All right, so why is this true? Basically, you take exactly the same derivation you had before, and you just take expectations over the valuations with respect to the prior everywhere. Okay, so you use linearity of expectation a few times. You know, expected welfare is expected revenue plus expected player utility. Here, now it's not a Nash equilibrium condition, now it's the Bayes Nash equilibrium condition. So, you know, at equilibrium, bidder I is doing whatever it's doing. If it wanted to, it could always bid half its value. Okay, that's one option. Okay? And so that's this deviation, okay, or half its value or the optimization that I showed. And then again, you just sort of, when the dust settles, you get exactly the same cancellations as before. Okay? So questions at this point. So at this point, I've actually shown you a full proof that for every first price auction environment, arbitrary correlated private values, every Bayes Nash equilibrium is within 63% has expected welfare within 63% of the expected maximum welfare. And moreover, I've shown you that that is the best possible number you can have in a statement of that form. Okay? So this is kind of the culmination of our single item auction discussion.
Is there an intuition for where this 1 minus 1 over 2 comes from? I see
Yeah.
the steps, but
Um,
it seems a little magical.
Do you have any thoughts, Jason? Do you have any intuition for 1 minus 1 over e?
If you look at your lower bound, it was your lower bound with the distribution that equalized the payoff of the player for any bid.
Right.
And that's just the distribution of value you get from calculating the area of loss with that distribution.
So it's a constant, in the language of a demand curve, it's a constant elasticity. of
I
one.
see.
In
I see.
the language of virtual values, it's a constant, it's virtual value of 0 beyond the end point.
I should say that, so you're right, so good. So that's in that one particular example. I completely agree with what you said. I feel like,
This is a more general, this is completely general.
right. But we also had that,
So why is that the worst possible example?
right. And also remember we had this seemingly different, we had, when we looked at multi-item, even full information, we had this more balls and bins reason that we were getting the 1 minus 1 over e. So I don't have a satisfying explanation for this. I don't really believe in mathematical coincidences, so there could be something that unifies all of these reasons, but I'm not sure what it is.
So going back to that example, though, this theorem is going to be tight for that example.
Right.
And so this theorem matches, that's inequalities are all going to be tight for that example. And so basically in this theorem, you're assuming you're kind of in that example. When you make the inequalities, you're basically saying, well, it's at worst that example. So that's sort of my intuition for it.
Yeah, I mean, another way of saying it is you can back out the example by just saying how could these be equalities, basically. Right, so you need this proof to be tight at every step to have a worst case example. It has the flavor of a complementary slackness type condition. But I still think there's a mystery here. Yeah. So. All right, everyone okay with the single item discussion? Okay. Let me skip this, actually. Let me skip all of this. So the last thing I want to do today is I want to talk about to what extent does this 63% extend to the multi-item case. Okay? And remember, I did state a theorem toward the beginning of the slide about this. But for the keen among you, there's actually sort of a stronger portion of the hypothesis in the theorem I gave you at the beginning compared to the first price auction guarantee, single item guarantee I just showed you. So that I need to explain. Okay, so how do we analyze the multi-item case? All right. So with multiple items, now all of a sudden we have to make assumptions about what valuations look like. Okay, so remember here, the private type is this full-blown valuation function. In the theorem I showed you at the very beginning, we were talking about submodular valuations. Here's the definition of a submodular valuation. The marginal value that you get an extra item is increasing, is bigger if you have smaller sets. So as T grows, as the stuff you already have grows, the marginal value of J decreases. That's a submodular function, okay? Everything I say in the rest of today will hold for submodular valuation functions. To keep things simpler, let me actually specialize to unit demand valuations. So this is where each bidder has a private valuation for each item, a VIJ for each item J, and intuitively it only wants one item. So if you give it a bunch of items, it just throws out all of the items except its favorite one. Okay? So those are unit demand valuations. Just to orient you, for those of you that have heard about, say, the gross substitutes condition, which is not important for today, but if you've heard about it, that's going to be more general than unit demand valuations, but strictly less general than submodular valuations. Okay, so ultimately that theorem will hold in particular for gross substitutes valuations, but it holds even under weaker notions of substitutes. Okay? All right, so this is going to be the setting. We'd like to prove a bound on Bayes-Nash equilibria of multi-item auctions, and boy would it be nice if we could piggyback on the work that we already did for single-item first-price auctions. Okay? So how might we do that? Well, so we can talk about the composition of mechanisms. So here I'm just going to be talking about a composition of m different first-price auctions, but it's a general notion. So it's a mechanism where basically all of the players play simultaneously and all of the constituent mechanisms. So in simultaneous first price auctions, every player submits m bids, one for each item. Each item is allocated to the highest bidder at that highest bid. You're participating in multiple auctions, you get all of the items that you win. Okay, so your allocation is the union of the allocation from the mechanisms, from the single item auctions, and you pay for everything. Okay, so the payment rule is just the sum of the payment rules of the constituent mechanisms. Okay, so what would it mean to piggyback on our single item analysis? Okay. Well, so here's the crucial inequality that we had for the single item analysis. Okay. So I'm using a term here, I sort of skipped the definition of it, but in the computer science literature, this condition is known as a lambda smooth auction. Okay. So this is what we saw was true with lambda equals 63% for a single item auction. It's possible to choose baselines, B star 1 up to B star n. Think about it being like bid half your value, so that this inequality holds. That gave us the guarantee for Bayes-Nash equilibria. So if we really want to try to be lazy, what we might hope to prove is that if we compose a bunch of mechanisms that are lambda smooth in this sense, then we get the composed mechanism is also lambda smooth. That means also for the composed mechanism, it's possible to choose baseline strategies. Now this is going to tell each player how to choose in every one of the mechanisms so that this same inequality holds.
So the statement of composition
Yeah.
is an idea that holds across games?
If you like.
It's a canonical way of composing
Sure.
games
Yep.
that's not related to the first. So what is the canonical method of composing games?
Okay, so I guess, I mean, the one thing which maybe, I mean, mostly it would be the same except possibly this, because this is not linear necessarily across the different auctions, right? So it's not just that I'm independently playing all these different single item auctions. My valuation is combinatorial. So I have, you know, preferences that cut across the different
Using a
games.
single unit.
I'm using it, so I'm using that it's sort of that there's an allocation rule for this to make sense, what I wrote. It's not really important that these, I mean, this definition makes sense for kind of arbitrary mechanisms, which are defined by an allocation rule and a payment rule. Yeah. Okay. All right, so this is the question. Okay. We know first price auctions are 0.63 smooth in the sense they satisfy this with lambda equal 0.63. Is it also true if you compose a bunch of them? Not obvious. Here's a way you might hope to try to prove it. Okay. Remember, we're thinking of bidders being unit demand. Okay. So they only want one item. So in an optimal allocation, a welfare maximizing allocation, each bidder only gets one item at most. Okay. So here's a way I could try to take as input, if you like, baseline strategies for each of the m individual single item auctions, and from it construct a baseline strategy for the same bidder in the composition. Okay? So these the assumed baseline strategies tell me a baseline in each single item auction. So the question is, you know, what should I do overall? So here's an idea. Okay? Think about the optimal allocation. Okay? So that's the same thing as a max weight matching. All right? If I'm bidder I and I don't get anything in the optimal solution, my baseline is just going to be to bid 0 everywhere. That's not interesting. But if in the optimal solution I get an item J, okay, so J is like my rightful item in the optimal solution, then that is the item in which I'm going to play my assumed baseline strategy. Okay, so think of the baseline strategy as bid half your value. So the proposed baseline strategy for the composition is look at the item that you rightfully deserve from the optimal solution, and whatever your value is for that item, bid half of it on that item and 0 everywhere else. Okay? So that's a proposed proof of how you get a baselines for the composition from baselines for the single item auctions. Yeah.
I must have missed it. Why can't you get 2 items
In the optimal, because it just by the assumption of the valuations. That's the definition of unit demand.
Oh.
So remember, we're thinking of bidders that throw out everything except for their favorite. So you may as well just give them one in the first place. Yeah. Okay. And it may seem like I'm really sort of abusing the unit demand assumption, but again, this actually extends with no problem to the submodular case. Okay, you're going to be bidding on not just one item, but on a bunch of items at once, but the analysis all still goes through. Okay. So this is the proposed way of how you might extend this so-called smoothness inequality to the composition. Okay? But there's an issue. Okay? This doesn't quite work. All right? It comes close, but there's a bug, and here's the bug. All right? So again, let's just think about those simple baselines where you bid half your value. So what did it look like in a first price auction? Bid half your value. B star I equals VI over 2. Okay? So this, of course, this baseline strategy depends on what I's value is. But notice it's what I'm going to call a private baseline in the sense that it does not depend on V minus I. Okay? So in this baseline strategy of bid half your value, you only need to know your own value. You don't need to know others' values. Okay? On the other hand, think about the baseline strategy I just proposed in the composition. I said, look at the item you rightfully deserve in the optimal allocation and bid half your value on that item. Think about that first step. If you only know your own valuation, you do not know the optimal allocation. Okay, the optimal allocation of items to the bidders depends on the full valuation profile. Okay, so for this to make sense as a baseline strategy, it must be in some sense that you know the full valuation profile. Okay? Now, it's not clear at the moment why this is sort of a problem, but I just want to point this out. There is a qualitative difference between the kinds of baselines I just proposed. I'm going to call them public baselines because they depend on the full valuation profile versus the private baselines that we used in a first price auction. Okay? So what's the big deal? Why do we care? Right? Maybe our theorem just still works and it doesn't matter. Okay? So here was our guarantee. Okay, so this is where we had a smoothness type inequality, and we derived a price of anarchy bound for any Bayes-Nash equilibrium with any correlated distribution. So there's a step in this derivation which doesn't make sense if there are public baseline strategies that depend on the full valuation profile rather than just on the bidder's own valuation. Any guesses? In other words, where in the first price auction analysis did we actually kind of crucially use the fact that the baseline strategies depended only on the bidder's own value and not on others' values? Yep.
That was an alternative strategy for the test.
That's right. That's right. You're going to say the same thing? Or? Yeah. Excellent. So it's in this line here. Okay? It's when we invoke the Bayes-Nash equilibrium condition. Right? So where does this inequality come from? It says, look, this bidder's using whatever strategies it's using at equilibrium. It could have instead played its baseline strategies. That's kind of what we're trying to say. With private baselines, that totally makes sense. It's true, this bidder could have always bid half its value. It was totally free to do that. So if it did it, it would have only less expected utility. With public baseline strategies, it no longer makes sense, okay, to switch to your baseline strategy. Why? Because to know your baseline strategy, you need to know not just your own valuation, but that of others. And at the time that you're choosing your bidding strategy, it's at the interim stage, not at the ex post stage. Okay? So in Bayes-Nash equilibrium, at the time you think about alternative bidding strategies, you only know your own valuation, you do not know the valuation of others. So from public baselines, you cannot extract a hypothetical deviation from a Bayes-Nash equilibrium. Okay? So that's the subtle problem. Okay?
Can't you make the baselines depend on what the others are doing?
On the other's values, or?
Yeah.
Yes, so you could, and that's indeed what we got. So that's what I'm calling public baseline strategies. What I'm pointing out is our previous theorem, our previous proof.
No, I understand.
Okay.
The previous proof,
I agree.
but you got something very strong. There was one profile that was,
Yes.
I mean, to argue the stars
Yeah.
could depend. Sorry, I'm not sure.
That's okay.
I'm not
I mean, I think you're anticipating exactly where I'm going. So,
Okay.
yeah. Okay, good. So what have we learned? So hopefully you understand there's this qualitative distinction between private and public baselines, and the proof approach for multi-item auctions seems to result in public baselines. And the point here is that our previous proof, at least unchanged, does not work with public baselines. Okay? So what do? Okay, so if we're feeling ambitious, we might hope to still just extend the 63%, full-blown to multi-item auctions. That would require either, maybe we can be more clever in our proof idea. Maybe we can have a different implementation that actually results in private baselines rather than public baselines. Then we'd be home free because we have our general result for private baselines. Or, maybe the problem is here, right? So maybe actually, even with a weaker assumption of public baselines, we can have a different proof which still leads to the same result. Those would be the two things we might hope we could do to actually salvage the 63% fully generally. But actually, the problem is not that we're not being smart enough. Okay? So the problem is that the full-blown generalization is just false. Okay? So there exists an example with unit demand valuations where the valuations are correlated, quite heavily correlated, okay, not independent, so that, in fact, the Bayes-Nash equilibrium gets a vanishingly small fraction of the optimal possible revenue as the number of bidders and items go to infinity. Okay? So not only is 63% not true for any Bayes-Nash equilibrium with a correlated valuation profile, but actually no constant bigger than 0 is true for arbitrary correlated valuation distributions. Okay? Now maybe you say, okay, well, it's kind of a lot to ask for every single correlated distribution. But again, remember that we actually had that for the single item auction. So it was natural to first try to get just as sweeping a statement here. But this shows that we cannot do that. Okay? We cannot get a guarantee for every correlated valuation distribution. So what's the plan? So the plan is, and actually, so this is, if you remember on the very first slide, when I showed you that theorem at the beginning, there was an assumption of independence among the valuations. Okay? So an analog of this statement will be true, but with a weaker conclusion just for independent valuations. And that's because we're going to have a weaker hypothesis, where we're going to have this smoothness inequality only with public baselines, not with private baselines. Okay? So let me just show you how to put these different parts together, and that will give us the desired guarantee, and we can wrap up. All right, so first of all, back to composition. We want to piggyback on what we know for first price auctions. We wanted to say that a smoothness inequality, again meaning this type of inequality, extends to the composition. That was not true with private baselines. Right? We had these first price auctions that were 0.63 smooth with private baselines. That counterexample shows that simultaneous first price auctions are not 0.63 smooth with private baselines. However, if you're willing to use public baselines, actually the composition just works. Okay? So now we can weaken the hypothesis. So suppose you have any family of mechanisms that are lambda smooth with public baselines. The composition is also lambda smooth with public baselines. And the proof is exactly what we outlined before. Okay, so given public baseline strategies for the constituent auctions, what you do now is you just look for the item that's rightfully yours in the optimal solution and then zoom in on that particular auction and use the assumed baseline strategy in that auction. And everything just works out. And it works out not just for unit demand valuations, it also works out for submodular valuations. Okay? So composition just works if you relax to smoothness with public baselines. Now, the other problem we have to resolve is that we don't, at the moment, have a price of anarchy guarantee under this weaker assumption. Okay, we only have a price of anarchy guarantee under the private baselines assumption. So we need a modified extension theorem, extension in the sense that it extends from pure equilibria to Bayes-Nash equilibria. So let's assume you have some mechanism, for example, simultaneous first price auctions, in which case lambda is 0.63. So suppose you have some mechanism that is lambda smooth with public baselines in the same sense. Then, with no other assumptions, for all product valuation distributions over unit demand or submodular valuations, in fact, lambda is a lower bound on the price of anarchy. Every Bayes-Nash equilibrium for every product valuation distribution gets a lambda fraction of the maximum possible welfare. Okay? This theorem actually takes a little work. Okay? Most of these theorems have very short proofs. This one, it's still not long, but it is sort of a page or a little bit more to prove this theorem. Let me just give you sort of the one idea. Let me remind you what the challenge is to proving a result like this and how the proof actually addresses it. So remember what the challenge was. So the challenge is that if you assume only these public baseline strategies, then at the point of the proof where you want to invoke the equilibrium condition, you want to think about a bidder deviating to some hypothetical deviation. And you want that deviation to be given by the baseline strategies. Okay? But again, in a Bayes-Nash equilibrium, you only know your own value, you do not know others' values. Okay? So it's not well defined to say I'm going to switch according to a public baseline strategy. You don't know V minus I, so you don't know your public baseline strategy. Okay, on the other hand, as a bidder, you may not know others' valuations, but you do have this prior. You know the distribution from which everybody else's valuations are drawn. So one thing you could do if you wanted is sample fictitious valuations for everybody else from the prior distribution. Now you have your own true valuation, fictitious valuations for everybody else. That gives you a valuation profile. Valuation profile tells you a baseline strategy. Now you could use that baseline strategy. Now it should not be obvious this is a good idea, that this is going to work. But I hope it is at least clear that this is a well-defined deviation in the Bayesian game. Okay, if I wanted, I could sample fictitious types for everybody else and then play whatever my public baseline strategy tells me to play. I could do that if I wanted. So if I did that, my expected utility would only go down. Okay? Now, the rest of this proof actually shows that this works. Okay, so you need to sort of manage all of these different fictitious types that all these players have invented for themselves, but at the end, it all works out. Okay? All right. So we're done. Let me review so you don't lose the forest for the trees. Okay? This was the statement we started with at the beginning. Okay? So remember what we're trying to do. We're trying to have an encoding of the maxim that when there are not strong complementarities, simple auctions do pretty well. Not strong complementarities is the submodular valuation assumption. 63% is the pretty well. Our particular simple auction is simultaneous first price auctions. Why is this true? Okay, the proof is just chaining together three things, all of which we've done. Okay? The first thing is that a single item first price auction satisfies the desired inequality. Okay, so it's lambda smooth with lambda equal 0.63, even as we saw with private baselines. Okay, and so therefore even for correlated valuation distributions in the single item case. Okay? That's step one. And again, let me remind you, this was like a half a slide. Okay? So this is kind of the only part of the proof where we actually use the details of the auction format, but it wound up being some basically trivial algebra. Okay? And I mentioned just so that you start getting the sense that these are all tools which, you're in a perfect position to use for your own applications. Okay? It's gotten to be a very user-friendly point. So this was a half a slide proving this. Then we had this composition theorem, which I didn't do in detail, but the proof there is also very simple, which says that simultaneous first price auctions are themselves 0.63 smooth. Now, however, with public baseline strategies. Okay? And then the one thing I sort of skipped was the proof of the modified extension theorem, but we can just use it as a black box. Now that we know from the composition that simultaneous first price auctions are 0.63 smooth with public baselines, we also know that for any product distribution over valuations, every Bayes-Nash equilibrium is within 63% of the maximum possible. Okay? So this is literally the full proof of this theorem. Again, with the caveat that there's a little bit of work hidden here. Yeah?
Given the simplicity of the first step,
Yeah.
you might think an obvious thing to do is to do comparisons across mechanisms, plug out the number analogous to 0.63.
Yep.
Find the best one.
Definitely.
Turn that into a maximization problem.
Definitely. And in some sense, when we talk about negative results tomorrow, it's going to be informed by that perspective. So we're going to ask, could you have a different auction format which would do better than this, which would do better than 63%? Now, you need to rule out the VCG mechanism, which would get 100%. But so you want to say something like anything which, with a message space which is not too big, cannot beat 63%. So those are exactly the kind of results we're going to be seeking next time. Yeah. Okay, so again, just to remind you, what was the whole point of this whole exercise? Arriving at this theorem. The goal was to make precise this folklore belief that with substitutes, simple auctions, while not fully efficient, are almost fully efficient in a precise sense. There's still this second folklore belief, which really is an impossibility result. It's really saying simple auctions are insufficient for complex preferences. That's going to draw on a field known as communication complexity. So I'll teach you the basics of communication complexity in the first half of tomorrow's lecture, and then I'll show you how to go from that to derive impossibility results for simple auctions. Thanks.
Seems that there's a key step in the sort of lemma to get the lambda smooth test. Is that to use the lemma to prove that is that the total surplus is the sum of revenue and the buyer's total surplus.
Mhm.
Does that mean that for auctions with reserve price we cannot use the same?
There are versions with reserve prices as well. There are also versions for some non-quasi-linear environments, like budgets. You have to make some compromises to get the theory to work. But so the short answer is quasi-linearity can be relaxed at least a little bit. But if you relax it enough, I think these probably break. The results probably break. Yeah.
In mathematics, there's often this idea of universality of the same concept appearing at multiple points, and you would try to convince us that this 63% is such a thing that might be appearing at multiple points. And I thought in probability theory, usually there are two common suspects if you ask for anything that is universal. And there is this normal distribution and the Poisson distribution.
Mm-hmm.
And in one of your examples, I thought there might be actually a direct connection to the Poisson distribution.
Sure.
That the probability is zero. So do you think there might be also a connection with the other examples that might explain why we see this?
So the connection is clear in the multi-item example, right?
Yes.
That's the one you mean. Yeah, I agree. It is clear there. It's an intriguing suggestion. I'll have to think about it. Off the top of my head, I don't see why, but I share your kind of way of thinking about it, that I want there to be a very simple reason for it, and why not the usual simple reasons? So I think it's a really good comment. So, yeah.
Thank you.
Okay.